So what we're going to talk about is we're going to look at nuclear chemistry. And so this is going to bring us back to similar things that we were talking about earlier in this semester in dealing with the atom and protons and neutrons and electrons. And what we've been talking about before is the bonding of atoms and how we join together to make compounds and H2O and CO2 and draw Lewis dot structures, ionic covalent bonding. And what was really important with that was the electrons. What we're going to do now is we're going to look at something that we consider nuclear chemistry. So if you think about nuclear chemistry, well, if we think about what this part of the atom is going to be dealing with, is we're going to be looking at the nucleus of the atom, and that's why it's considered nuclear chemistry. We're not so much worried about the electrons, but more about what we find in the nucleus. So you guys should have your notes out and be following along. We're just going to fill out the first little bit of this, and it's a lot of review for today, but it's helpful for review so that as we move forward, you guys kind of have that idea of, okay, what did we talk about in the past, what is in the nucleus, and what is the importance of those particles that we find in the nucleus. So the nucleus, if we remember, is comprised of two different subatomic particles. All right, we have the protons and the neutrons, and those are the ones that are in the nucleus. Again, this is just review, so just take a look. All right, pay attention, and let's review some of the things that we've talked about. So the first thing we're going to look at is if you remember how we identify and how we kind of do what we call element shorthand. Right? And that is, if we take a look at carbon here, right, there's two numbers that we can associate with carbon. There's this number on the top, which is the bigger of the two numbers, 12, and the number on the bottom. So if we remember that number on the top is what we consider our mass number. And the mass number deals with the particles that have mass, which both protons and neutrons have mass. So the mass number tells us the number of protons plus neutrons that we find within the nucleus of the element. We also have the atomic number, which is down here, which is number 6. And the atomic number really tells us the number of protons, right, in the nucleus of the atom, or electrons, right, if it is neutral. If it's a neutral atom. If it's not a neutral atom like we saw with ions, then it doesn't tell us how many electrons, but what we're going to focus on, not so much are the electrons in this section, because again, we're dealing with nuclear chemistry, we're going to worry about what's in the nucleus. Now, also something for us to review is things that we talked about, which were isotopes. So isotopes, remember, were atoms of the same element, but they had different number of neutrons. So with them having different neutrons, they had to have not a different atomic mass. Oops. They had to have different masses because of the different neutrons. So if we take a look at three naturally occurring isotopes of uranium, we have uranium-234, we have uranium-235, and we have uranium-238. So if you look at the periodic table, what I want to do is make sure we understand and can tell, okay, how many protons does each one have and how many neutrons? So if we remember, the number of protons is told to us by the atomic number. Uranium, because it has an atomic number of 92, that tells us that each one of these has 92 protons. All right? Then what's the difference and why do we get 234, 235, and 238 is that is the number of neutrons. So if we take a look then at the number of neutrons that we're going to find for each one, for 234, the number of neutrons we would have would be 234 minus 32. So that would be 142 neutrons in uranium-235. For uranium-234. For uranium-235, we would get 143 neutrons. And then for uranium-238, we would get 146 neutrons. And so isotopes are the same elements, same number of protons. As we can see here, we have the same number of protons for all three of them, but different number of neutrons. And the bigger that the isotope is, 238, the more neutrons that we have. Okay? Now, the thing that we're going to get into for today is an idea of, okay, well, what are these neutrons then used for? So if we think about some of the things in the nucleus, protons we know carry the positive charges. And so if we take a look in this diagram, all right, these are our protons, the ones that have the positive charges. Neutrons carry a neutral charge, where there's no charge specifically, but then electrons are going to be the ones that carry a negative charge. So here's what we know. Because the protons have the positive charge here in the nucleus, and the electrons have a negative charge, because they're opposite charged, there is an attraction together. And so electrons are actually held around the nucleus due to the opposite charge from the proton. They are attracted towards one another. But the idea then, or the question would be, well, if these protons are all positively charged, why do they stay in the nucleus? Because if they're positively charged, they want to repel from one another. They want to get away from one another. So how then do they stay in the nucleus if they're all trying to push each other away? Right? And that's what we're going to look at in nuclear chemistry, and that's some of the questions that we're going to answer today. So, what is the purpose of a proton? Well, what we've talked about in the past is it determines which atom or which element an atom is. If we go from 92 protons to 6 protons, we go from uranium to carbon. The number of protons is what determines the element. So then what is the purpose of the neutrons? That's really the main question for the day. And what we should see is that they help hold the protons together in the nucleus. So, what we're going to look at then are the two forces that are really at play then within the nucleus. And what we're going to do then later in class and for your homework tonight is you guys are going to look at how the number of neutrons changes as we go through the periodic table. So, the first thing that we're going to look at is just nuclear chemistry. Understand that nuclear chemistry is the study of nuclides, or where nuclides are what we consider just nucleuses. And so we're not worried about the electrons, we're just worried about the nuclides, right, that exhibit trends to break apart. And so nuclear chemistry is when we look at these nucleuses that will spontaneously change. So understanding then what holds that atom together, and again that's what we're going to focus on for today, is there's two forces that we're going to look at inside the nucleus of an atom. The first one is the electrostatic force, right? This force is one of two things. It can be either an attraction force or a repelling force between the charged particles, right? An attraction force, as you see on your notes, if we look, right, an attraction force, and go ahead and write this in your notes over these pictures, is if we have two protons, or what I would like you to add as well, is like charges. These like charges are going to repel. Two protons would repel one another. The forces would try to push each other apart. Two electrons would repel one another because they're like charges. They would try to push each other apart. And the opposite charges, though, are what hold things together, and there's an attractive force between those. So with the electrostatic force, the distances between the particles actually plays a big role in terms of how strong that force is. The short distances are a really strong force, so the closer that those particles are, the stronger that force is. Where then the longer distances, or the further apart particles are, the weaker that force becomes in terms of either an attracting or repelling. So if we think about then, what's inside the nucleus, the protons, all within a single nucleus, they're all trying to push each other away, right? Because they're all like charges, so they're all trying to repel one another. So the question then, again, how do the protons stay in the nucleus? That doesn't make sense, because if they're all trying to push each other away, then why are they staying together? Right? So then there's a second force within the nucleus, which we consider something called the strong force. Right? And the strong force is only attraction. There's no repelling. It's only pulling things together. And it is acting between particles within the nucleus. It really has, something to do to their mass. So similar to gravity, right? Where because you are on Earth, you are attracted to the Earth because you have mass. And if you didn't have mass, you wouldn't have this gravitational attraction towards Earth. And so it's similar idea with the strong force, where the strong force with the short distances, it's actually a very strong force. It's extremely difficult to break this strong force. As long distances, similar to electrostatic force, it gets weaker and weaker and weaker, almost goes to none. Right? And what this strong force does is it really helps keep the nucleus from flying apart. So the more particles we have, the more mass that we have in the nucleus, the more we're able to actually hold that nucleus together because of this attraction. So again, when we back here, there are then attractive forces that are keeping these protons in together, and so that nucleus actually stays together. So within the nucleus, there are two main forces, right? And there's that strong force, which acts between neutrons and neutrons. It acts between neutrons and protons, and it actually acts between protons and protons because they have mass. But there's also that second force, which is a repelling force, and that's due to the electrostatic forces that we have. Right? Now, we don't see this in our notes, but we're actually going to create this in our homework. But what is actually important is this a proton to neutron ratio within the nucleus of an atom. As that ratio goes from 1 to 1 to greater than 1 to 1, meaning more neutrons than protons, it's actually, we need those neutrons in order to keep that nucleus together. So what you guys are going to see, and what you guys are going to see in your worksheet, is you're going to start graphing how many neutrons there are in comparison to protons within the nucleus of almost every atom that we have on the periodic table. Right? So the smaller nuclei that we have, the more stable that they are. And so they only need a 1-to-1 ratio. There's not a lot of protons repelling one another, so we don't need a lot of neutrons to kind of hold them together. But as we go up on our periodic table, we actually start to see that there's more and more and more neutrons per every single proton. Right? So a 1-to-1 ratio that we see actually down here is meaning if there's 1 proton, there's 1 neutron. So if there's 4 protons, there's 4 neutrons. There's 6 neutrons, there's 6 protons. There's 12 protons, there's 12 neutrons. But as we go up into this higher range with elements with higher number of protons, we actually get different ratios, right? And so we see, for every 1 proton up here, we actually have 1.5 neutron. That doesn't mean that there's a half neutron, because you can't have that, but that just means that we have more and more and more neutrons than what we had before, right? And what we'll look at is we'll actually look here that at number 83, and we'll talk about this again after we make this graph, that the number of neutrons really, if we get big enough, right, because of all these protons trying to repel one another, we eventually get to a point where these neutrons can't hold things together, and things are going to actually go into radioactive decay and become radioactive. And so that's what we're going to be looking at in nuclear chemistry. So this is just a review, again, about kind of what is in the nucleus, looking at the forces that are acting in the nucleus, and then just introducing the idea that as we go across the periodic table, as we increase the number of protons, meaning as we go from element to element to element to element, the number of neutrons is actually going greater than a 1-to-1 ratio, as we see here. And that 1-to-1 ratio, or why it's going greater than that 1-to-1 ratio, is to help hold the nucleus together and stabilize that nucleus. And that as we get bigger and bigger and bigger, we have radioactive elements because we don't have enough neutrons. We don't have enough strong force to actually hold that nucleus together.